Hi everybody, this is the X-ray diffraction masking automation project by the ME35 senior design team. I am Nicholas Watkins, and my team members are Michael Ciocco, Robin Marihugh, and Gavin Shawfield. For some background, SKF Aerospace is a manufacturer of high-performance bearings used for critical applications in the aerospace industry. Bearings are routinely pulled from the production line in Falconer, New York for testing to verify material properties of the heat-treated steel. The retained austenite and residual stresses from the heat treatment must be characterized to ensure accuracy of their rated specifications. In order for them to do this, an X-ray diffraction or XRD testing is done to analyze the sample material at its surface. It is required for them to coat the samples in a lacquer masking when removing material from the sample in order to get measurements at different thicknesses. Currently, the masking is done manually by the operators, which takes an extensive amount of time out of their day and bottlenecks the process. The size and geometry of the samples can also vary as well as the size of the unmasked testing window. Our problem statement is to design a system that automatically coats the desired surfaces of the bearing samples. The process for our development of the final design started with concept generation, which included different ideas such as how to apply the lacquer onto the samples, how to move the samples around, and how to grab them. Followed by that is our experimental testing of the lacquer on our samples to verify any findings. From there, we were able to select our concepts based on those test results, and from there we began CAD modeling and then performed calculations in FEA simulations. Our experimental testing was done to characterize the lacquer masking processes. Several different tests were performed, including different application methods, control of the masking area, as well as dilution of the lacquer with a thinning agent to find the optimal fluid properties for the chosen application method. The application and drying times, masking film thicknesses, and the quality of coatings were all recorded for each sample tested. From there, we were able to do a dip coating analysis once we had our selected application method of dipping, which required a set retraction speed determined from the lacquer parameters. We performed FEA simulations on our design components, which gave us detailed information of the stresses acting on the components, and also checks to ensure that no parts fail during operation. In our simulations, points were selected to be verified with hand calculations, and those hand calculations were used to calculate forces and stresses determined on the drivetrain, and also from the required speed as well. The basin and the mixing system for the lacquer was also analyzed using FEA. These tests were performed on the lacquer solution basin and the mixing plate, which ensures that the drag forces and the weights do not cause failure. Force and stress calculations are also performed on the linear actuators that create the agitating motion, as well as the respective mounting hardware. With all those components analyzed, we were able to model the complete system, which resulted in our final design. This design included custom components as well as many off-the-shelf parts. It incorporates several subsystems together, including the sample dip coating, the lacquer mixing and agitation, as well as the sample loading and unloading. The production throughput of the samples was then calculated from experimental testing results for the application drying times, as well as the calculated speeds necessary to achieve our desired coat thicknesses. And from those numbers, we were able to confirm our desired throughputs and that all of our specifications were met.